Hello students, in my last lecture I talked about polarography. Now in this lecture we will talk about amperometry, which utilizes the same equipment which is used in polarography. Difference between polarography and amperometry. In polarography, current is measured as the potential is varied, whereas in the amperometry, the current is measured when a fixed potential is applied for a short time. The outline of the lecture will be introduction, the detection methods, principle of the technique, apparatus used, factors affecting amperometric titration, the types of amperometric titrations, advantages, disadvantages of amperometric titrations, and then applications of amperometric titrations in industries. The detection of ions in a solution on the basis of electric current or changes in electric current is called as amperometry. In other words, amperometric titration is a form of quantitative analysis in which the equivalence point is determined through the measurement of the electric current produced by the titration reaction. In amperometric titration, the end point is determined by measuring the current variation between the two electrodes, either two indicator electrodes or one reference electrode and one indicator electrode, which are immersed in the solution that contain the analyte. The potential between the two electrodes is kept constant as the titrant is added. Indicator microelectrode, as I told you, is same, that is dropping mercury electrode, and the reference electrode used in amperometry is saturated calomel electrode. The potential of the measuring electrode is sufficient to ensure a diffusion current for the electroactive ion or substance. We can also say that first we should record a polarogram for the reducible ion, and then we must apply a potential at the plateau of the wave for carrying out amperometry. The detection methods are single potential amperometry, pulsed amperometry. Let us discuss them one by one. The first one is single potential amperometry. It is the simplest form of amperometric detection in which a potential is applied between two electrodes positioned in the column effluent or solution containing the analyte. The measured current changes as an electroactive analyte is oxidized at the anode or reduced at the cathode. Now, the current is used to detect weak acid anions such as cyanides and sulfide. In the case of pulsed amperometry, it is used for analytes that tends to foul electrodes. With each analysis, the foul electrodes reduce the signal and causes a need for cleaning of the electrode. Here, the working potential is applied for a short duration, generally for milliseconds, followed by higher or lower potentials, which are used for cleaning the electrode. So, after each run, we have to clean the electrode because it is poisoned or foul. The current is measured while the working potential is applied, and the technique is used to detect amines, carbohydrates, reduced sulfur species, etc. Now, we know that according to Ilkovic equation, ID is equal to 607 n d half C m raised to the power 2 by 3 t raised to the power 1 by 6, where ID is average diffusion current during the life of a mercury drop and it is measured in microampere. 607 is the constant, n is equal to number of electrons involved in the electrode reaction, which may be for oxidation or reduction. D is the diffusion coefficient of the ion and it is measured in centimeter per second. C is the concentration of the electroactive species and it is measured in millimole per liter. M is the flow rate of mercury from the capillary, it is measured in milligram per second, and T is the drop time of mercury to fall from the capillary and it is measured in second. You must remember we have discussed Ilkovic equation during polarography, and this is the fundamental equation which is used in polarography as well as in amperometry. The diffusion current is directly proportional to the concentration of the electroactive species, because we can see from this equation that ID is directly proportional to C if all other factors of the equation are constant. The diffusion current at a particular voltage is measured as a function of volume of the titrating solution. A supporting electrolyte is usually added to ensure the sufficient conductivity to minimize the migration current. The apparatus which is used in amperometry is a simple apparatus, because here we have to apply a potential and therefore, we require a simple Pyrex glass 3 naked flask, a dropping mercury electrode, a reference electrode, a microburette and a gas outlet tube for nitrogen. You can see here the simple apparatus used. Here we have a source of applying potential, that is usually a battery, and here we use a potential divider so that the desired potential can be applied. The two electrodes are dipped in a solution containing sufficient supporting electrolyte, and this A represents current measuring device, usually a meter, and here this microburette is used for adding the different volume of the titrant. Mercury is noble metal, so there is no reaction with constituents of electrolytic solution, and therefore, there is no chance of contamination, as fresh surface of mercury is formed after each second or after the fall of each drop. The results are highly reproducible and the electrode is ideally polarizable. It is possible to apply more negative potential at mercury in comparison to normal solid electrodes. Diffusion current which is observed is directly proportional to the concentration, that is, diffusion current increases with increasing concentration. However, we require potential maintenance, that is, the potential applied should be constant throughout the experiment. Now, let us come to various types of titration, that is, types of amperometric titration. The first one is titration of electro-reducible ion with the electro-reducible ion. Second, titration of non-reducible ion with the electro-reducible ion. Third, titration of electro-reducible ion with the non-reducible ion. Then the titration involving the redox reaction, and finally biamperometry. So, let us come to them one by one. The first one is titration of electro-reducible ion with the electro-reducible ion. Here both are reducible. So, titration of electro-reducible ions with electro-reducible ion causes displacement and the decrease in the diffusion current is noticed. The main reason for decrease in diffusion current is the decrease in the concentration of titrant. Then the titration of electro-reducible ion with the electro-reducible ion, again we are considering the same one. Here after the addition of titrant, an increase in diffusion current is observed due to the increase in the concentration of titrant. For example, let us consider titration of lead ions versus dichromate ions. In this case, if we look at the curve here, this is diffusion current and volume of the titrant on x axis. If we monitor the change in diffusion current, we see that initially the diffusion current decreases and at one point it starts increasing. We are increasing addition of dichromate ion. So, first there is decrease in diffusion current due to the removal of lead ions, because when lead ions are added they form lead chromate which precipitates, and then after this the increase in diffusion current is due to the continuous increase in the concentration of dichromate ions added, and therefore, the end point is very sharp, because here we are getting almost V shaped curve and we can easily determine the end point at the intersection of two straight lines. Then let us come to titration of non-reducible ion versus electro-reducible ion. In this case, initially the diffusion current of the non-reducible ions is minimum and the diffusion current does not change by the addition of titrant to the titrate. After the end point, further addition of titrant shows an increment in the diffusion current. For example, if we take titration of chloride ions against silver ions. In this case, as we can see here, the diffusion current is practically constant in the beginning and then at one point it starts increasing. We are adding silver ions and therefore, if we plot volume of the titrant and diffusion current, we can see a clear cut increase and the intersection of the two straight lines gives us end point. Here the initial part of the titration curve is almost a horizontal line and the curve starts rising after the end point due to further addition of silver ions, which starts reducing and you can see a clear cut end point in this case. Then let us come to titration of electro-reducible ion with the non-reducible ion. The diffusion current is observed by the electro-reducible ions. First, there is decrease in the diffusion current due to the decrease in electro-reducible ion, and at the end point all the reducible ions precipitated and removed, thus shows the constant diffusion current. Example is titration of lead ions against sulphate ion. Here you can see, if we plot diffusion current against volume of the titrant, which is sulphate ion, we can see initially the diffusion current decreases and at one point it becomes constant and you start getting almost horizontal line. The end point is determined by the intersection of the two straight lines and we can say here that with decrease in the concentration of lead ions, the diffusion current goes on decreasing, and when all these ions are removed, the diffusion current becomes 0 because there are no lead ions available in the solution. Now, the only residual current flows through the cell and the current becomes practically constant and remains horizontal in nature. Let us come to titration, which involves the redox reaction. Based on the oxidation and reduction properties of substances, the titrate, that is oxidant, is titrated with the reductant as titrant. The reductant added to the oxidant is completely oxidized. The diffusion current reaches to the minimum and then becomes constant. The electrons given by titanium 2 plus are taken by iron 3 plus. The intersection of the two lines shows the end point. So, let us now consider the example of ferric ions against titanous ions. In this case, our titrant is titanous ions, and if we plot diffusion current against volume of the titrant, we can see here that the diffusion current is continuously decreasing, and at the end point it becomes finally constant and we start getting almost horizontal straight line. The intersection of the two linear segments gives us the end point. That means the plot shows the decrease in the diffusion current with the decrease in the concentration of the oxidant. Let us now come to biamperometry. Biamperometry is introduced by scientists Fock and Bowden in 1926. The titration requires two indicator electrodes, you can see here, in place of DME and saturated calomel electrode which we used in amperometry. Here we are using two indicator electrode and the rest of the circuit is same. This is the battery which is attached to a potential divider, and this is the sliding key. By moving this key we can adjust the desired potential, and here this is a galvanostat which provides us information about the current. When the redox system is present, before and after the endpoint, this method is used. Here you can see that one electrode works as anode and other works as cathode. The volume of the titrant and diffusion current, when they are plotted, we can see here that the current initially decreases and then at one point it starts increasing and we get almost V-shaped curve. The two electrodes are immersed in the electrochemical cell and a fixed potential with a difference of about 10 to 20 millivolt is applied among these electrodes through the adjustment of resistance variable potentiometer. At the end point, one electrode is depolarized until the oxidant and reductant is completely oxidized or reduced. The example is Karl Fischer titration, in which the amount of water or moisture is determined. Let us now come to advantages of amperometric titration. The first advantage is that the end detection point is very easy. We can easily detect end point in amperometric titration. Second, automation is very easy because you require a very simple apparatus in the case of amperometry. Third, the rapid and simple apparatus. Fourth, high selectivity. In the case of amperometric titration, the selectivity is very high because we are carrying out titration at a fixed potential. Very dilute solution of the order of 10 raised to the power minus 4 molar can be readily determined, at which many potentiometric titrations no longer yield accurate results. Next advantage is temperature independent. There is no effect on amperometric titration by variation of temperature. The reaction can be reversible or irreversible, it does not matter. The amperometric titration will provide you significant and similar results. Titrations can be successfully carried out where the solubility relations are such that potentiometric or visual indicator methods are not much good. Supporting electrolyte minimizes migration current, which originates due to electrostatic attraction of analyte ions by the electrode. It is reduced to a negligible level by the presence of high concentration of supporting electrolyte like KCl. Next, non-reducible ions can be easily determined, which is not possible in the case of polarography. In polarography, we require groups which are reducible because we get S-shaped curve only for the reduction of groups. Then the disadvantages of amperometric titration: it requires the specific equipment. We cannot carry out like simple titrations where burette, pipette and beaker are needed. We require a potential divider for the amperometric titrations. Sometimes interferences causes inaccuracy in result. This normally happens when the two ions oxidize or reduce at very similar potentials. It should have voltammetric information because unless you have information of complete reduction potential, we cannot apply amperometric titrations. This is applicable in the quantitative analysis of the mixture of metal ions, which means if we have more than one metal ions, we can easily use this amperometric titration by selecting the potentials. It is applicable in water analysis by Carl Fischer reagent, and it is used in the analysis of alloys in various industries. For quality control in food stuff industries, amperometric titrations are widely used. Direct determination of cyanide in drinking water is possible by using amperometric titrations. The electrode consists of a glass tube of length nearly 15 to 20 centimeter and 6 millimeter in diameter. At one end of this tube, a platinum wire of nearly 5 to 10 millimeter length is fused and it is exposed to the solution from the one end of the glass tubing. The electrode is then mounted on the shaft of the motor and the motor is rotated at a constant speed of nearly 600 rpm. Electrical connection is made to the electrode by copper wire passing through the tubing to the mercury covering the platinum wire seal. Let us have a look at the rotating platinum electrode. We have a glass tube at the bottom to which the platinum wire is fused, and for the connection purposes mercury pool is provided, which provides a connection with platinum wire, and one end of this pool provides a copper wire for connection purposes. The metal rod is then connected to a motor which moves the electrode and at a fixed speed of about 600 to 700 rpm. Now, in this case the diffusion current is nearly 20 times larger than that observed at DME, which permits the measurement of the very small concentration of ions. The reason for increase in the current is stirring, which permits more ions to reach the electrode surface. The rotating platinum electrode can be used at positive potential up to about plus 0.9 volt, whereas DME can be used only up to plus 0.4 volt due to the oxidation of mercury. This means that large potential range is available for oxidation at platinum electrode. The electrode is simple to construct. Steady diffusion state in this case is reached quickly, and successive determination of chloride, bromide, iodide can be carried out by using rotating micro electrode. To summarize, we have discussed about amperometry, the detection methods, the principle of the technique, apparatus which is used, factors which affects amperometric titrations, types of amperometric titration, advantages and disadvantages of amperometric titrations. Applications in various industries have also been explored. In the next lecture, we will discuss potentiometric titrations and we will compare amperometric titrations with potentiometric titrations.